Let us now discuss the charge controller. It is an important PV battery and load interface. So if you consider a PV panel or a PV module, and to that we have a direct connection of the battery like this. So we discussed about this direct connection of the battery. If the PV panel and battery are compatible, then you don't need any further electronics. However, the PV panels are not used generally to only charge the batteries. They are operated to also supply to the load, and most of the time the PV panels are supposed to be operated at maximum power point. So in general, you would also have the load which is connected across the PV panel. Now consider the IV characteristic, VT, terminal voltage versus the current. Now if you have a IV characteristic like that, and I will draw the PV also with the same color and say that the operating point, the peak power operating point optimally should be near here. Now let us say insulation has changed. Insulation has changed means there will be a change in the short circuit operating point, and let us say you have another curve. The VOC point varies logarithmically, so you will not see that much of a change as compared to the short circuit operating point. So I have this IV curve, changed IV curve for the new insulation and the PV curve, and the optimal desired operating point would be somewhere corresponding here. So let me mark that point. Now it's still for the different insulation, I have an operating point like this. So if you see the locus of the peak power points or the locus of the maximum power points, the operating points will be along somewhere in this almost vertical, near vertical line. So if I draw a band like this, okay, this band would be the zone of operation. This will be the zone of operation for peak power point or maximum power point zone of operation, where in this region of operating point you will be at near MPPT, and that is sufficient for most of the applications because of a slight flatness in the hill of the power versus V curve. If we now say that the region of the operating point should swing in this narrow band near the peak power operating point, then obviously all these operating points are not supposed to be used because you will be way below the peak power operating point, and likewise on this side also these operating points are not supposed to be used. So if the operating point has to hover around here, direct connection will not work. Direct connection of the battery here will not work. You need to have some electronics here which will properly manage the power flow from the PV to the battery, from the PV to the load, between the battery and the load, and all those things. So you need a unit there, and that unit is called the charge controller because it controls the flow of charge and it steers the flow of charge. So the main job of the charge controller is that it steers the power flow from the PV module between the battery and the load. Before we discuss the circuit of the charge controller, let us understand the functional logic of the charge controller. How does the charge controller behave? How does the charge controller function? Consider this condition when the battery voltage is above a preset Vmax voltage. We will preset this voltage. When the battery voltage is greater than that, then we say that the battery is in the charged condition. When the battery has reached the charged condition, we would like the battery to discharge into the load only and not get any more further charge from the PV panel. So at that time, you can disconnect the battery from the PV array and connect it only to the load. So the condition would be then disconnect battery from the array or from the PV array, but let it be connected to the load. Now if the battery voltage is less than a predefined V minimum voltage, let us define this. So the battery voltage is less than that, we don't want it to discharge any further, but we still need to take charge from the PV panel. Then disconnect the battery from the load. So you know that the battery is not going to discharge into the load, but it is still connected to the PV panel, which means that it can charge up from the PV panel. Another third condition, if the battery voltage is in between Vmin and Vmax, the predefined minimum and the max voltage, then during that condition both the PV and the load can be connected to the battery and they all will be operating within the zone of the maximum power point of the IV characteristic of the panel. So under that condition, both the PV array and the load are connected to the battery. So this is the simple functional logic of almost all charge controllers. So majority of the charge controllers will follow this logic, and let us try to understand this logic and build the circuit schematic for this. Let us now put the functional logic into the form of a brief circuit schematic, conceptual schematic, by trying to understand what this Vmin and Vmax are from the point of view of the IV characteristic. Now let me have this Vt versus It, and I have this characteristic, and we said that we would like to operate in the MPPT zone. So a region of a set of operating points here which are near MPPT. Now this lower voltage point, we will define it as Vmin, and the higher voltage point will define it as Vmax. Now if the battery voltage is within this, then the PV panel, battery and the load are connected. If the battery voltage is less than this, then you know that the battery is not in the charged condition, and therefore the battery has to get disconnected from the load. So for battery voltage less than this, battery has to get disconnected to the load. It will get directly connected to the PV panel, so it will be charging with almost the full PV panel current. And in this region above Vmax, we don't want the battery to charge any further, we don't want the operating point to shift any further to this side, and we will connect the battery to the load and disconnect the battery from the PV panel. So that is the logic. So now let us draw the conceptual circuit. We have the PV panel. Let me have a switch, a battery, and connect it like this. Now let me have another switch and connect the load in this fashion. So let me call this as S1, and let me call this switch as S2, switch 2. Now this voltage is the battery voltage VB. So this is VB. So this is the conceptual schematic. Now let us see the various modes. We had put three conditional statements. One is when the battery voltage is greater than Vmax, when the battery voltage is less than Vmin, and the battery voltage is in between. So just let us see how this conceptual schematic works in these three modes. So in the first mode here, let us define V battery greater than V max. So during the mode when V battery should be greater than V max, we saw in the condition that if VB is greater than V max, then disconnect battery from the array. So that is the condition that we have applied. So we should connect the battery only to the load, because battery is fully charged. Let it discharge to the load and let it not get further charged. Let this be open. So the PV panel will not be charging the battery, but the battery on the other hand will continue to discharge from the load. So that is what is indicated in this flow of the current here. In the second mode, we had the condition battery voltage VB less than Vmin. So the battery voltage is less than Vmin, meaning it is in this region, the battery voltage, which means the operating point will be somewhere here. So we need the battery to charge up, so which means we need switch S1 to be on and S2 to be off, and therefore only S1 will be connected and the battery will be connected to the PV panel and get charged up. In this condition here, you see that the load is not having any connection either to the battery or to the PV panel. Load will not be supplied with power. Do you want this? Let me get back to that after the final condition, the third condition. So here in the third condition, we say battery voltage is in between Vmin and Vmax. Vmin is less than or equal to V battery, less than or equal to Vmax. So the battery voltage is in between these two values. So under that condition, it is, which means that it is in the zone of near MPPT. So all will be connected. Both S1 will be connected and S2 will be connected, and there will be current flow in both the load, the battery from the PV source. Now I'm coming back here and I would like to state that during the time of this mode 2, when battery is less than Vmin, it is now connected to the PV panel. PV panel is charging up the battery, which means the operating point is somewhere here. The load is not having any power source connected to it. What happens to the load? You could connect the load in this fashion, and then there is a buffer capacitor here which will do some buffering, and I will call this as S3. So one can have this kind of a structure to see that during the time when the battery is low, PV panel is charging up the battery and S3 is connected here, and it is PV panel is also supplying to the load. But understand that this S1 is a unidirectional current flow. Current will not flow out of the battery and again through S3 into the load. So that is one caution that you have to apply. S1 is unidirectional switch. There can be current flow only in this direction, not in the other direction, and PV can supply current and therefore the power to the load during this time. So the condition is that same condition, when VB is less than Vmin, S3 is on. So we will say S3 is on, and during this condition S3 doesn't come into the picture, so obviously S3 is off in this condition and that doesn't come into the picture. So this is a modification that one can do during the time of this condition when the battery voltage is less than Vmin. Then there can be some amount of power flow going into the load through the switch S3, provided S1 is a unidirectional switch. However, in most charge controller circuits, you will not find S3. It will just be only S1 and S2. Keep it simple. we will be discussing the implementation of this circuit, because most of the time the operating point will be hovering in this region. Both greater than Vmax and less than Vmin condition is the extreme condition. Majority of the case it will be here, and therefore it will be one of the switches S1 and S2. S3 will not come into the picture. I have here the entire circuit schematic of the charge controller circuit. You see these two switches are relays. They have relay coils associated. The relay coils are actually turned on and off by BJTs. There is one BJT here, another BJT here, and they are driven by op amps. And Zenards are basically used for setting the preset Vmax and Vmin limits. Now, how does this circuit operate? Let us reconstruct this circuit and you will understand how this circuit has come about. Let me start with a clean white board. You have the PV panel, PV array, and the PV array is connected to the load or not. And we also have the battery in between like this. So this is the battery. So this is how the circuit is. Here we had one switch and there is another switch here. Let us place that. So switch S1 and S2, and now we will make both these switches normally closed. By normally closed means most of the time in operation we want both the switches to be on. Battery is between Vmin and Vmax, and the operation is such that PV is supplying both to the battery and to the load, and battery is acting as a energy buffer. Switches S1 and S2 are relays. They are driven by relay coils. So there is a relay coil here which will drive switch S1. So when this relay coil is energized, then this switch S1 will be open. If this coil is not energized, then that is the normal operating condition. S1 will be closed, normally closed. Likewise, relay S2 is energized by this coil, and as for S1, when the coil is energized, S2 is open. When the coil is not energized, S2 is closed, normally closed. So these are relay coils. I will mark them here, and I will indicate that this is an NC relay, normally closed relay. That's what it means. Under unenergized condition, the switch is closed. So this is also NC. So let me now draw a resistance with a Zener here, and I will also put another two resistances like this. So this midpoint here, at the midpoint of this attenuator, will be considered as representing VB, and the midpoint of this and the Zener is considered as Vmax. So this attenuator here, just a voltage division for this battery voltage, will represent VB, and from the battery, because the battery voltage can be varying, so I will need to take a fixed reference voltage. So if I use a Zener, then this would be a fixed reference voltage, and I will call that one as Vmax. Now both this you buffer it with op amp. So let me pass VB through a buffer. This is a voltage follower, and Vmax also I will buffer it. The reason you buffer it is that this is high input impedance. Input impedance is high, output impedance is low, so any resistance that you use will not affect the output side portion of the circuit. So now these two I will give it to a comparator. So I will pass the VB voltage value through a resistance, then give it to the plus input of the comparator, and the minus input I will give the Vmax, and the output of the comparator I will pass it through a resistor to the BJT. Now the output of the comparator and the plus of the comparator I will put a resistance. This is important because you need to give hysteresis between the upper lip trip point and the lower trip point. I will explain that later. Now the base of the transistor is driven by this op amp. So you are connecting it to the negative rail, and the collector is connected to this relay coil, and the relay coil is energized by the battery. So let me have that. This battery, I will give this symbol, and for the ground, circuit ground, imaginary ground, I will give this symbol. This is what is used for powering up the op amps. So I will power up this op amp, power up this op amp by the battery voltage. I will call this one as Q1, and this is VC, control voltage. See, the relay coil has a large resistance and a large inductance also. So when you switch off the relay, there will be a huge inductive kick. To prevent that, you have a freewheeling diode here like this. Don't forget to put that, otherwise your BJT here will blow. So put this freewheeling diode like this. Now you see how it operates. Now I have this potential VB, which is sensing the battery voltage, and I have this Vmax, which is a fixed voltage coming from the Zener terminal. Buffered. So this is VB, this is Vmax. So whenever VB is greater than Vmax, comparator, this is a comparator, VC goes high. So when VC goes high, Q1 turns on. When Q1 turns on, there is a relay current flowing through this, so relay is energized. This will open. So our condition, when VB is greater than Vmax, switch S1 will open. So that the battery is only discharging to the load. But when the switch opens out, battery is wholly supporting the load, and therefore there will be a drop in this potential. Because of this drop in this potential, this will come down and then probably become lower than Vmax, and this will keep on switching. This continuous chattering is not good for the relays, so you put a hysteresis. Now that is why this hysteresis is coming into the picture. So the moment VB goes greater than Vmax, this will go high, turn on, this will open, this voltage will go slightly low because it is supporting the entire load. And even if that goes slightly low, because of this hysteresis, there is a lower trip point. Only if that goes below, only if VB goes below that lower trip point value as decided by this hysteresis components, you will again see the NC switch closing again. So hysteresis is very important here. Use that and put that appropriately. Now coming to the other portion of the circuit, let me connect a resistance and a Zener. Now this resistance and Zener is used for determining the other reference voltage, which is Vmin. So I will buffer that also and pass it to the comparator. So I will have the op amps powered by the battery supply. I will have another buffer. I don't need this buffer actually, but I am just showing it for completeness. I could always pick up VB from here. But anyway, I will use this VB, output of that one buffered. This is Vmin. So the output of Vmin, I connect a resistor, and these two I pass it into a comparator. Vmin I give to the positive of the comparator, and a minus of the comparator I give VB. And the comparator is powered by the battery, and the output of that is given to BJT, and as before, the BJT collector is connected to this relay, S2's relay coil, and you call this as Q2 and this is VC2. Don't forget to put a freewheeling diode across the relay. Now this portion of the circuit, how does it operate? When VB goes less than Vmin, when VB goes less than Vmin, VB connected to the minus terminal goes less than Vmin, this will go high. When this goes high, Q2 goes on. When Q2 goes on, this relay is energized. When this relay is energized, S2 opens. So when VB goes less than Vmin, we want S2 to open. According to our logic, S1 to be closed so that battery is getting charged. So that is the logic that works here. Here also we would like you to use hysteresis here. So you can connect a resistance between this and the output and have an hysteresis, because as soon as this is opened, there will be a shoot up of this voltage and again chattering will result. Therefore, it is good to connect a resistance across this and put a hysteresis so that the trip will occur even if the voltage shoots up. The again the trip will come back depending upon the lower trip point and the upper trip point determined by this hysteresis. So in this way, this charge controller circuit works. So whenever the VB is greater than Vmax, you will see that this will open out, this will continue to remain closed, and whenever VB is less than Vmin, look at this polarity, this will open out, this will remain closed. So when VB is between Vmin and Vmax, both, if VB is less than Vmax and VB is greater than Vmin, both these are off and S1 and S2 are closed. So that is the logic that we want. And all the electronics here are powered by the battery voltage. So therefore you don't need any other extra power supply apart from the battery voltage. The battery voltage is compatible. If the battery voltage is very large, then you will have to have a small DC-DC converter to generate this power supply which you are using for this op amps and the relays. Instead of the switches S1 and S2 being relays, you can also replace them with power semiconductor devices. You could use MOSFETs and BJTs also. But most of the time the system, the circuit is operating in the operating zone near the MPP. Therefore S1 and S2 will be on, and therefore these relay coils are not energized. Q1 and Q2 are off. There is not current flowing through the Q1 and Q2. So least amount of power being drawn during the condition of MPP, which will be the majority of the time period that this system will be in that zone of operation. And therefore this is a pretty efficient circuit, and the relays will come into picture only under the extreme operating conditions, when VB is going greater than Vmax and when VB is going less than Vmin. Only then the operation of these switches come into the picture. Otherwise they are not in the picture. So only then the operation of the relays will come in, and the number of cycles of operation will be very low. It will come for many years, because the relays have greater than 10,000 cycles of operation, so it will last many years. So therefore this is a pretty using with relays is a pretty useful circuit, simple circuit, and very inexpensive. Let us say that we would like to replace the relay with a power semiconductor switch like a BJT. So let me erase this portion of the circuit and replace the switch by a power BJT. I am using a PNP because I am putting the PNP on the high side, and I can do rail side switching. So let me put a resistance like this, and I need a resistance here between the base and the emitter. And one more modification here, we need to give VB to this and Vmax to here. So now the logic will be okay. You see, when you see that now Vmax is given to the positive, VB is given to the negative. So normally VB is less than Vmax, so therefore this is high, Q1 is on, and the base current flows, this will be on. Now when VB goes greater than Vmax, negative goes higher than plus, this will go low, Q1 will switch off, there is no base drive, this will switch off. So when VB is greater than Vmax, we want this to switch off, and then we want battery to discharge into the load. So that way you can replace the relay with a power semiconductor switch also. Instead of a PNP transistor, you can use a P-channel MOSFET too. I will leave it to you to do the replacement of this with a power semiconductor switch like a PNP transistor or a P-channel MOSFET, and appropriately adjust the logic here.